All right, guys, so we're going to have a quick conversation today about reaction coordinate diagrams, which are really just a tool for us to look at and talk about the amount of energy that is going into a reaction or coming out of a reaction and what that energy is being used for. So let's go ahead and jump into our um, PowerPoint. And the way that this relates to kinetics, of course, is that a lot of what we learn from reaction coordinate diagrams is how much of our energy is going into activation energy. And so that's going to tell us about how quickly or how slowly a reaction is going to progress. So as we're trying to understand the kinetics of a reaction, it's really helpful to be able to visualize the energy changes that are happening throughout that process. And so we use something called a reaction coordinate diagram in order to graph the energy versus the progress of the reaction. So just a quick reminder that when we talk about activation energy, we're talking about that minimum amount of energy that's required for a reaction. And usually that energy is going into breaking the bonds that are already in existence in order for new bonds to be formed. So in that process, we have to put energy in to break those bonds or possibly to make a transitional state. And then once we reach that activation energy and new bonds can be formed, now we're moving down the hill on the other side. So we're able to go from this peak where we've put energy in, down the hill on the other side, and ultimately to our goal. So just like the ball can't roll up the hill without us hitting it hard enough, our reaction can't begin without that input of activation energy. And usually that activation energy can come from the environment, from the surroundings. It can pull enough energy from the surroundings if it's warm enough. Sometimes it requires a little something more, like the spark in your engine that starts the spark from the spark plug that starts the explosion that causes the cylinder to press down and therefore the car to roll forward. So we have that activation energy. So when we look at an activation or a reaction coordinate diagram, we see that hill, we see that activation energy. Okay, in this particular reaction, we're looking at a reaction that actually just rearranges bonds. So this is a unimolecular reaction. But in order for this to happen, first bonds have to bend, then it has to create what we call the activated complex. So this is the thing that forms in the middle. Sometimes we call this an intermediate, especially if something new has been formed. And then as it begins to form the new bonds, it starts to release energy, and then we arrive at our products. So when we look at any reaction coordinate diagram, there are certain things that we can see. This difference between the reactants and the products in terms of energy. This is the overall energy change for the reaction. And we call this the enthalpy change. This difference between the reactants and the activated complex, that is our activation energy. So we may see a reaction coordinate diagram that is not like this one, where the delta E is not negative, where we go from reactants to products, and products would be higher. That would indicate an endothermic reaction. Anytime our reactants are higher than our products, we are talking about an exothermic reaction. So this reaction is going to have a negative delta E. This reaction is going to give off energy. If, as I said, the products were higher over here, then that would indicate that not only do we have to put in the activation energy, but we actually have to put in energy beyond that just to keep the reaction moving forward. And again, those can happen just at room temperature. Okay, so let's talk about the different pieces of our reaction coordinate diagram. We see the energy of the reactants here. This is the potential energy of the reactants. We see the energy of the products, and therefore the difference between the two of them is the change in enthalpy. Okay. We also can see this high point on the diagram, and this high point is what we call the activated complex or the transition state. And sometimes in this case, we can see that it's actually a broken bond and that things are rotating. You may sometimes see an activated complex that is two molecules that have bonded together and bonds have not yet broken. Or you may see one bond broken and another bond yet to be broken. Activated complex is just what we have in the middle. It is the transition state, but the transition state is always found at that high point. This difference in energy between the reactants and that high point, this difference right here, is the activation energy. And that is really the barrier, that's that hill that we have to overcome in order for the reaction to happen. So we can read a lot of things out of a simple reaction coordinate diagram. Okay, this is a simple reaction coordinate diagram. This is a one-step or a elementary reaction. We know that many reactions don't occur as elementary reactions, but instead as multi-step reactions. So let's take a look at a reaction diagram from a multi-step reaction. So here's the energy level of our reactants, our hydrogen and our chlorine diiodide. So we have the reactants and they have to get up and over this first activation energy. And you'll notice that these two activation energies have sub A1 and A2 on them. That's just telling us it's the activation energy for step 1 and the activation energy for step 2. And you'll notice that in this particular multi-step diagram, that the first step requires a higher activation energy. Because it requires the higher activation energy, that means this is going to be the slower step. So when we start talking about reaction mechanisms, we'll come back to the idea of higher activation energy is going to be the slower step and therefore the rate determining step. So here we have a transition state. Now we've formed a new product. We have this HCI and we have HI. And these are our intermediates, okay? Now we have a new reaction happening between those intermediates. And we have a faster step with a lower activation energy. And that produces iodine and hydrogen chloride, monochloride, monoiodide. And so we see that overall, if we were to look at the activation energy for the overall reaction, it would be this activation energy. It would be the largest activation energy, even though this happens in multiple steps. Because we go from a high potential energy of reactants to a low potential energy of products, this is an exothermic reaction. It's going to give off energy. But depending on how big this activation energy is, it may be fast or it may be slow. Okay, so that's one example of a multi-step reaction diagram or reaction coordinate diagram. Now we have a new reaction coordinate diagram, and we can see that this one is an endothermic reaction. We have a low energy of our reactants and a higher potential energy of our products. We can also see that this happens in multiple steps. The activation energy of step 1 is this difference between A and B, and the activation energy for for this one is from this bottom point to this top point. And so we actually see different activation energies. Overall, the activation energy for this reaction would be the difference between A and D. So it has a significant activation energy, but it does happen in 2 separate steps. In this case, this step would be our slow step because it requires the most energy. And so this would be our rate determining step. Okay, and just a couple more examples of multi-step reaction diagrams. So this is a single step reaction diagram, and you will sometimes see multi-step reactions condensed down so that this reaction coordinate diagram could be either this reaction or this reaction because they have the same overall activation energy. They have different transition states and different slow steps, but they have the same activation energy. And so we can see that we have lots of different processes that can give us the same activation energy. In the same way, all three of these could also be represented by this reaction coordinate diagram. So this would be the overall reaction. These might be different mechanisms for that multi-step reaction. So very often we'll only see the overall reaction coordinate diagram, but it is important that you guys can recognize a multi-step reaction coordinate diagram, that you can recognize that if the difference between reactants and products is negative, that it is exothermic. If the difference between reactants and products is positive, that it is endothermic, that you recognize that the tallest activation energy is the slow step, and is the overall activation energy for the reaction. And that's it for reaction coordinate diagrams. Just let me know if you have any questions. Thanks.